All right, so taking a look at this function here, we're going to go through looking at all the different important aspects of it. I'm going to start over here on the right. So what degree is our polynomial here that we drew a picture of? The third degree. So our parent function would simply be x cubed. Because remember, a parent function just means it's the most basic form of that kind of function. So in this case, cubic function is what we're dealing with. So our parent function, most basic one, is just x cubed. End behavior. We started writing end behaviors in a little bit more of a sophisticated notation, if you will. So as x approaches positive infinity, that means our right side of our graph. As x approaches negative infinity, that means the left side of our graph. So let's look at the right side. Which way is our graph going? To infinity and beyond. And then our left side, the graph is going where? Negative infinity, because it's going down. Those are our end behaviors for these ones. When we talk about end behaviors, it's an odd degree of 3. It's got a positive leading coefficient, so we knew that the left side was going to be down, the right side was going to be up, based on what we talked about last time. So what are the zeros of this function? -4, -2, and 0. -4, -2, -0. So I'm looking next, domain and range. What would be our domain here? Element of the reals. Or if you prefer interval notation, negative infinity to positive infinity is the other way that we can write that. Our range for this one? Y is the element of the reals. Again, negative infinity to positive infinity if you prefer the interval notation there. So just to review a couple other things about functions. Is this a one-to-one function? No, why not? Fails that horizontal line test. Right there, my horizontal line would hit my graph 3 times. Definitely fails it there. So not one-to-one. Is it onto? Yes. Why is it onto? It uses all the range values. Now remember, if it weren't even a function, you would never even test to see if it was one-to-one or onto. Because it's not even a function to begin with, so it can't be the other two. All right, let's take a look at turning points. Does anybody remember what the special names were for these ones? Yes, awesome. Relative max, relative min. Why do we call them relative max and min? Yeah, they're not the absolute highest and lowest, but for that area of the graph, it's a high and a low point. So it's a max and a min there. Now they look like they hit nice numbers, right? It looks like the max is at -3.3. It looks like the minimum is at -1, -3. But are they really? Let's find out. So in the calculator, there is a highly underused function that you guys got to get to use this a little bit more. It's going to help you out so much on that Regents exam. Second trace. It can find your max and mins for you, so let it. So I'm going to go for my minimum value first, so I'm going to select choice 3. And then if you look at the calculator, it's asking for left bound. So it's asking you to get your little blinky guy to the left of your minimum, because again, I'm looking for minimum. So my little blinky guy right now is to the left of my minimum, so I'm going to hit enter. Now what's it asking me for? The right bound. So now I'm going to go over to the right side, and I'm going to hit enter. And then it asks me for a guess, but do we ever really waste our time with guesses? No. Hit enter. So where's our minimum actually at? I got x is negative 0.8. My y is negative 3.1. So that is where my actual minimum is. So go ahead, find the maximum. So do second trace, choice 4. Find that max value where it actually is. So go to the left side of it, right side of it, enter. What do we get? There we go, negative 3.2, then 3.1. Now, when we're sketching pictures of graphs, is it really going to matter exactly where those are? No, because sketch always means what? It's guess. It's pretty close. You don't want to be off by a lot, but it doesn't have to be 100% exact. When do you think this would be really important? This is going to be really important on a multiple choice question on that Regents exam. That button should be your best friend when it comes to these kinds of questions on that Regents exam, because you just do your second trace and find it. It will have the decimals every single time on those questions. Bless you. So then our last ones here, increasing and decreasing. This has 2 increasing sections, 1 decreasing section. So I'm going to go to my decreasing section first. It decreases from my maximum value down to my minimum value. I just got those x values. So my maximum was at negative 3.2. My minimum was at negative 0.8. So that was my decreasing piece, from my max down to my min. Remember, we always use x's for those increasing and decreasing parts. So can anybody tell me one of the increasing intervals? Very good. Negative infinity to negative 3.2. If you wrote it as an inequality, it would just be x is less than negative 3.2. Either one works. One's interval, one's inequality. Negative 0.8 to infinity and beyond. Or x is greater than negative 0.8. Those are your 2 ways of being able to write the same thing. So again, just a little review of different things we've talked about. They all still apply to our polynomial functions and our graphs of them. So what we're going to be working on today is we're going to be combining our end behaviors that we were talking about last time. We're going to put it together with multiplicity of zeros. And we're going to create some sketches of graphs today. So let's go back to the first page underneath that warm-up that we started with. So the number of zeros that a polynomial function has is always equal to the degree. So if you have a 5th degree polynomial, it's going to have 5 zeros. You got a 20th degree polynomial, it's got 20 zeros. My example from the third one in the warm-up, that's going to have 42 zeros. So whatever the degree is, that's how many zeros it's going to have. I'm good. So if x equals a is in fact a 0 of the function, then things we know are that x minus a is a factor. Remember, we were referring to this as the root value. So changing the sign of it and putting it with x, that's the actual factor. Because x equal a is a 0, that means f of a would equal 0. If I plugged my root value in, I would get a remainder of nothing. And then the point a0 is on the graph. Remember, when you plug a number in, that combined with its remainder is a point on your graph always. So the zeros of your functions could be real numbers or they could be imaginary. Today we're going to focus on the real ones. Next class we're going to focus on the imaginary ones. Imaginary zeros do not cross the x-axis. So what that ends up looking like is you'll have a graph. You'll have a couple of roots on there. And then the graph kind of does like this funky little dip thing right here. That means you have imaginary roots right there. You can't actually find them from the graph, but it does a little funky dip in there so you can tell that you have them and that they exist. So then a graph has at most n-1 turning points. So what that means is if you have a degree of 5, you have at most 4 turning points. Those turning points are also referred to as extrema. And I say the phrase at most because let's say, for example, I have the graph of y equals x cubed. That graph looks like that. Does that have any relative maxes or mins at all? No. So that doesn't mean it's absolutely going to have that many, but it could. So this one being a third degree, it could have 2 max or mins somewhere in there. This one actually ended up not having any. It's just saying at most. So it could have at most 2. So let's take a look at some examples that we have here. So starting off with my f of x there. First thing, if you're trying to create the sketch of your polynomial, is you need to consider your end behaviors. So this was last class. End behaviors means we need to look at 2 things. We got to look at the degree and we got to look at the leading coefficient there. So of my example, f of x, what is my degree? I heard somebody say it. Degree is a 3. That's in standard form. So my largest exponent. What's my leading coefficient? 1. So that means it's an odd degree with a positive leading coefficient. That means the left side of my graph will be pointing down. The right side of my graph is going to be pointing up. If you're just drawing the sketch, you don't have to get into the fancy notation for your end behavior. You just have to remember which way it's going to end up going. That's going to help you when you're actually making your graph. F of x is going to have a total of 3 zeros because it's a degree of 3. And it's going to have at most 2 extrema. Remember, it could have none, it could have 1, but 2 is the max. So now part C, let's actually solve to figure out what the zeros of our polynomial are going to be. So we're going to have to do some factoring. So we always look first, is there a GCF factor here? Yep, what is it? X. So x times x squared minus x minus 2 equals 0. How does that trinomial factor again now? Perfect. X minus 2, and then x plus 1. So remember, those are our factors. Sometimes you may see them referred to as linear factors. Why in the world would they call them linear factors? No, they're not. Because their exponents are all 1. Exponents of 1s, remember, those are your linears. So these are all linear factors because their exponents are all 1. So then finishing this off, our zeros, one of them would actually be at 0. X equals 0 is one of our zeros there. And then we got x equals 2. And then we got x equals negative 1. So those are the 3 zeros of our function. So then part D over here, we're going to sketch a picture. So I'm going to put a dot at 0, because that was one of my zeros that I got over there. I'm going to put one at negative 1, and then a third one at 2. So when we're drawing our graph, we should also take into account what our y-intercept is going to be. What would be the y-intercept based on our equation? 0, because remember, your y-intercept is your constant term. This one didn't have a constant. There was no number at the end. So our y-intercept is at 0. So then putting it all together, as we said back in the first part, our end behavior's left side's supposed to be down, right side's supposed to be up. So my end behavior all the way on the left, I'm just going to draw that going straight down from my 0 there. So now this needs to come up, and then it's going to curve back down to hit my next 0. Now, because it's a sketch, we don't really need to worry about where that little maximum value is going to be happening. We just curve it back down. And then from here, it's going to come back up, and it's got to hit my other 0 at the 2. And then my right end behavior is that it's going up, so I'm just going to draw my arrow going up. And that's the sketch of my graph. So let's take a look at multiplicity of zeros and what ends up happening on our graphs there. So looking at f of x, first thing they want us to determine is how many zeros exist. So looking at your equation of f of x, how many zeros should we have? 3. Part B, find the zeros algebraically. So x cubed minus 4x. Set that equal to 0. We'll have to factor. So do we have a GCF? X. And then we got x squared minus 4. You could factor dots, yes. Or you could just add your 4 over and then square root both sides. I kind of think it's a little faster that way. So if we add our 4 over, we have x squared equals 4, square root both sides, and we get plus minus 2. So then part C, they want us to determine how many x-intercepts do we have. Now, however many different numbers you've got as your zeros, that's how many x-intercepts you're going to have. So we got a 0, a 2, and a negative 2. So we have 3 x-intercepts there because we got 3 different numbers. And then part D, they want us to sketch a picture. I already took care of that for you. I already drew the picture of the graph on there for you. So if you take a look, here's our 3 zeros. It was an odd degree, so if you notice our end behaviors are opposites. My left side is going down. My right side there is going up. That's what our picture ends up looking like. Nothing really too fancy. So let's look at letter or function g there. How many zeros should g have? 4. Let's find the 4 zeros algebraically. So x to the 4th minus 4x squared equals 0. What's our GCF? X squared. So we got x squared minus 4. So when I set my GCF equal to 0, we get x equals 0. X squared minus 4 gives us x equals plus minus 2. So how many x-intercepts do we have, though? We have 3 x-intercepts. But up above at part A, we said we were going to have 4 zeros. So what happened? Why do those not match? That right there made the 0 what we call a double root. Your 0 is a double root. It's there twice. So we still have 4 zeros. We just have 0, and then we have 0 a second time, and then our positive 2 and our negative 2. So 0 is counted twice because it had an exponent of 2. So what ends up happening, if you look at our graph here, instead of crossing the x-axis at 0, it's doing a little bounce. So it comes up to the x-axis, it hits it, and then it goes right back down. And that's because 0 is a double root. So that's how it affects our graph there. So our positive 2 and our negative 2, those just cross right through the x-axis like we're used to. But that 0 ends up bouncing because it's a double root. Well, let's move on to our next one, h of x. So how many zeros will h of x have? 5. So I'll find those algebraically. So our GCF this time is x cubed. And then that leaves us with x squared minus 4. So we get x equals 0, and then x equals plus minus 2. So how many x-intercepts do we have? 3. So if we take a look at our graph, again, negative 2, positive 2, that looks exactly the same. But what's happening here at 0? Does it look like what happened at 0 over here in our first one? No. Kind of lingers, kind of zigzags. I like to call it a wiggle. It kind of wiggles there. Because this time our 0 is a triple root. It's there 3 times. So we still have 5 zeros. It's just 0, 0, and 0. Those are the first 3 roots. And then we got our negative 2 and then our positive 2. So on the graph, to indicate the fact that 0 is there more than once, it kind of does like that little wiggle as you go through the 0 at your x-axis. And that's how it indicates it's there more than once. All right, let's see what happens with this last one here. So j of x, how many zeros? 6 zeros. Go ahead, find them algebraically. So again, we end up with 0 plus minus 2. Almost like I did it on purpose. So how many x-intercepts do we have? 3. So how many times is 0 there now? 4. That's what our exponent is. So 0 is a root 4 times. Does it look different on the graph? Compared to this one? Yes, it does look different. I call this a bouncy wiggle. Very mathematical term there. So if it's just a 2, it just goes right up, bounces right back off. If it's more than 2, so if it's going to be to the 4th, the 6th, the 8th, it kind of goes up, lingers a little bit, as somebody said, and comes back down, or it just kind of bounces up and wiggles a little bit and then comes back down. So the graph does kind of indicate how many times a root is there. You just have to look for the signs. Yep. It does just kind of expand a little bit more the more times that 0 is there as a root. Yep. So our multiplicities of zeros, what ends up happening is you look at the exponent there. That tells you how many times that root is a 0. So if k, which is your exponent, if that is an odd number, then the graph crosses the x-axis at that value. Sometimes it's a wiggle, sometimes it's a straight line if it's just to the first power. And then if k is even, it bounces off. You'll hear some other people use the phrase touches the x-axis at that point in time, but it definitely does not go through the x-axis there. All right, so let's put this all together. Let's look at our two graphs on the last page here. So we have one equation in standard form, and then we have one in factored form. So we're going to go through both kinds of forms that we have here. I have my little list there of what we need to do in order to be able to get to our step number 5, which is sketching. Step number 1 wants us to determine our end behaviors. So again, end behaviors are figured out by looking at the degree and the leading coefficient. So my example 1 there, what degree is it? Fifth degree. Leading coefficient is -2. So again, odd degree with a negative leading coefficient means the left side would be up and the right side is going to be down. Now, just because we do have our quiz coming up next class, let's practice our fancy notation. So again, as x approaches positive infinity, my function would go to negative infinity. And then as x approaches negative infinity, my function approaches positive infinity. All right, step 2, determine the number of zeros and the number of possible extrema. So how many zeros will we have? 5. How many extrema could we possibly have? 4. It's always one less than your zeros. All right, step 3. Now we find our zeros algebraically. So we'll set our polynomial equal to 0. What is our GCF? -2x cubed. So we get x squared minus 6x plus 9 equals 0. So does that factor again? Yes, it does. So what does that trinomial factor into? X minus 3, x minus 3. So we get 0, and then 3, and then 3. Those are our 3 zeros. Of course, 0 is there how many times? 3 times. So fourth part says to determine the multiplicities, right? Yep, determine multiplicities for each factor. I recommend making like a little chart. Does not matter which way your little chart goes. So I write my factors, or my root values that I got. I only had 2 of them this time around. So the 0, as we just said, has a multiplicity of 3, because it had the exponent of 3 there. So because it's an odd multiplicity, will it cross or bounce at the x-axis? Odd is cross. So that's going to cross. But it's going to cross with like a little wiggle, because it's not to the first. And then our 3 is there how many times? 2. So that one's going to bounce. All right, so I'm going to start off with putting dots at my 0. So at 0 and then at 3. Do I have a y-intercept to take into consideration here? No, because there's no constant value, so it's going to be at 0. So that part's all good. So as we said, the left side is going to come from being up above. So I'm going to put that there, and as we said, it's going to kind of wiggle its way through 0. So I don't want to go straight through 0. I kind of curve it a little bit through 0, a little bit of a wiggle. And then what should it be doing at my x equals 3 again? We said it's going to bounce. So I got to curve this back around so it can bounce off my 3 and go back down. Your middle part in here might be a little bit different. Some people extend it down further. That part doesn't really matter. You just got to wiggle through the 0, curve back up so you can bounce off the 3. From the multiplicity. Odd multiplicities cross, evens bounce. All right, let's try it again. This time in factored form. Okay, first one. Got to figure out end behaviors. Yep. This one, factored form, we figure out the degree by adding the exponents. So 3 plus 2 plus 1 means that this is a 6th degree. How do we figure out those leading coefficients again? Yeah, multiply all the leading coefficients from the factors. So it would be -1 cubed. Those exponents play a part in it too. Times 2 squared times 1. So it would be a -4. Even degree with a negative leading coefficient. Remember, both those sides are going to be pointing down. So again, let's practice our notation. I want positive, I want negative. Both going down. All right, second step. Figure out our zeros and our extrema. So how many zeros are we going to have? 6 of them. How many potential extremas will we have? 5. Step 3, we're going to actually figure out what our zeros are. So I'll take my polynomial there, I'll set them equal to 0. Now, because it's already in factor form, they really helped us out. Now we don't have to do that whole factoring step. So negative x plus 5, we set that equal to 0, solve for x. And what does x equal? 5. That 2x minus 2, what does x end up equaling? 1. And then the x plus 4, we end up getting x equals -4. So that takes part in the multiplicity section. So again, multiplicity comes next. I'm going to make my little table. So because this factored form had an exponent of 3, that means x equals 5 has a multiplicity of 3. So since it has a multiplicity of 3, is it going to cross or bounce? Cross. And it'll wiggle a little bit as it does it. So then the x equals 1, what does that have a multiplicity of? 2. So will that cross or bounce? Bounce. And then the x equals -4, 1, so it will cross. All right, so I'm going to start off -4, 1, and 5. So I start off with my dots on my zeros. Will we have a y-intercept to consider this time? Yeah, we will. It won't be 0. Remember, this is in factored form. So our y-intercept, we figure it out kind of like we did our leading coefficient. So that's going to be 5 cubed times 2 squared times 4. You multiply the constant terms from within your factors. So what does that give us? 5 cubed times 2 squared times 4. Mm-mm. 2,000. 2,000. So now, does my graph actually show 2,000? No. So I'm just going to kind of, as long as you indicate you know it's supposed to be really high up there, that's all you really need to do. Because again, it's a sketch. We don't have to be 100% accurate. So now, end behavior's left side should be going down. Again, because of our multiplicities, what are we doing through the x equals -4? Are we crossing or bouncing? Crossing. So we're going to go up. It was only to the first, so it didn't have to have a wiggle. And I'm going to go up to my y-intercept. So then what's happening at my x equals 1? If we look down here, that one's bouncing. So we're going to have to come down and bounce off of that. And so then at the 5, it's going to cross, but because it was a 3, it's not like a straight cross. We got to make it wiggle a little bit. So I got to curve this around so I can wiggle through there. A second little wiggle. That's my arrow. Right here? Oh, that's part of this wiggle. I was just